Thank you, Arpin, for the introduction. And yes, and today we're going to kick off the new sort of segment within the series. It's going to be a relatively short segment, just two, short compared to the last energy modeling and thermal comfort one. But we're going to have two sessions on this. This is part one of two, and we're going to just be focusing specifically on daylight and electric light modeling, as well as what goes hand in hand with this is glare analysis, which we'll get to in the next session, and really getting into physics-based rendering. So just to give an overview so you guys know what to expect for today, we're mostly going to focus on modeling daylight, on just some very simple studies of modeling daylight, just so that those people who are not as familiar with how to model daylight in Honeybee, you'll at least get a sense of how to do that. And those of you who are more advanced, hopefully maybe you'll appreciate some of the myths that will be challenging with respect to certain daylight strategies, some very common daylight strategies such as light shelves and light diffusing materials, skylights. We're going to get all into that today. And then finally at the end of this, it's going to be a relatively small part just because it really is still very much a beta, but I know we kind of advertised this session saying that we'll at least give a short description of the Honeybee for Dynamo and a short demo of that. So we're going to have, at the very end, we're just going to do a short demo of that with the caveat that it's really the Dynamo version of Honeybee is very much so a beta right now. And while I'll show you a working example, I'm going to spend the last few minutes probably discussing what still needs to happen for it to be, well, for one, for it to no longer be a beta, and two, for it to be as good as the Grasshopper version. So, all right. And then, so that's going to be all today, and then next Tuesday we're going to get, I'm going to more specifically cover, just because this daylighting, this basic daylighting and the Dynamo is going to take up a long, pretty good chunk amount of time, that we're going to do electric light modeling in the next one, specifically with the goal of mitigating light pollution. That'll be our sort of design example, although there are so many cases where you can use the electric light modeling. And then we're going to sort of talk about how we use the same engine that we're using to evaluate daylight is essentially, it's a rendering engine, just like what all of our other renderings are produced with. And I'm going to show you how to make not just photorealistic, but real physics-based renderings that are really true to the colors. And then we're going to use those same images, those same renderings that are physics-based to evaluate glare. All right, so with that, this is kind of going to be the schedule for today, so I'm going to give actually probably even briefer than 10 minutes, just a really rough, because a lot of you already sort of understand what Illuminance are if you're at this advanced of a workshop, but just a really brief recap of that. And then we're going to talk about, we're just going to set up a basic daylight model, and then we're going to one by one go through and try a bunch of different strategies for improving the daylight in a simple office. Just so that we can debunk some of the myths maybe related to some of these strategies. And then finally, at the end of it, I'll just briefly show you how to do annual daylight simulations. So we're going to be actually just using some simple Illuminance simulations for all of these other studies just to keep it fast and iterative. And then finally, the last 20 minutes, we'll go into Honeybee Dynamo, and I'll explain a few things that need to happen for us to have a full Dynamo version. Okay. All right, so again, this is all going to be, both this session and the next session are all going to be Honeybee, working within Honeybee. Of course, Honeybee is built off of Ladybug, so there are going to be some Ladybug components. But specifically, the components that we're working with, pretty much all Honeybee components are going to be on this branch over here. So the stuff that relates to daylight, glare, visual comfort. And we just finished a total of 4 segments on energy use and thermal comfort modeling. So we really exhausted that a lot. And this session and the next one are just going to be using that. And then after that, we'll get to the Thermal window. But we're only working with the daylight and glare in this session. All right. Or even just daylight. Glare is going to be the next one. So just a really brief recap. A lot of you, I mean, this is going to be a review for a lot of people, so I'm going to go through it very fast. But just to understand what exactly, so the metric we're going to be using to evaluate how good daylight is for our studies is called Illuminaance, and that's supposed to be an I, not 3 L's in a row. Yeah, dang Arial font. All right. Well, in any case, yeah. So we're going to be using this Illuminaance metric, which really just to understand it. We have a series of metrics that are kind of related to Illuminaance, and really all of them. I mean, some of them we're already kind of familiar with. Like a lot of you are already familiar with solar radiation or the energy of the sun. that is coming and hitting surfaces. But both illuminance and radiation, all these things can be, they're all calculated by the same computational method, which is just called backwards ray tracing. Which, I mean, we'll get into a little bit more detail about what that means later, but really all these metrics that have to do with the solar intensity and the intensity of light, they're all using this basic principle, which is the same underlying principle of all rendering engines, of all, and of all radiation illuminance values. So, all right, so I already said that we can calculate radiation by tracing basically sun rays and rays from the set of points out to a sky. And those units, if you guys are already familiar with that, because we've worked with that in Ladybug, those are kilowatts or watts. So that's the actual, those are energy values of solar intensity. And what we're going to be working with today is illuminance. Now, illuminance is directly related to solar radiation, usually. There's a pretty good, correlation. The only very important difference between illuminance and radiation is that illuminance is essentially, it's kind of a measure of energy, just like radiation, but it is weighted for just the visible spectrum of the sun. So when we look at radiation, we are looking at all of the energy over the entire solar spectrum here, which includes a lot of wavelengths of light that we don't see, that our eyes don't perceive because they're infrared. We only register their presence as heat. And so illuminance is basically just, it's directly correlated to radiation, but it's evaluating just the intensity of energy within this window in which we can see, in this window of visible light. And the units of illuminance are lumens per meter squared, or lux. If you're in the U.S., it's the same metric that we'd use in IP. Is called foot candles. But I'm going to be using lux here just because I think it's a little bit more internationally understood. And so that's really what we're going to be using to evaluate here, because we're not going to use solar radiation to evaluate how well our daylight is. We're going to be using illuminance, which is really just targeted to evaluating how good things are in the visible spectrum. And then finally, here's a zoomed in version of that just so you guys can see. But all that's in black here is the full solar spectrum, if it wasn't clear before. And what's colored here is just the visible spectrum. All right, so, and finally, there's one other metric which we're really not going to get too much into today, but it's also measured in lux, and that's just called luminance. And the distinction between these two, actually, I mean, really, if these two have ever confused you, that's okay, because they are the same unit. They're measured pretty much in the same way. They're both, essentially solar energy weighted with the intensity of light. But the only key difference here, it's really just a small semantic difference, is that illuminance is measured on the plane that light, unlike on the desktop. So that is the measure, that's the amount of light that falls onto that desktop. Whereas luminance is the amount of light that is getting actually into our eyes, going through our pupils. And so it's really, the difference is only, a matter of reflection off of the desk surface. They're pretty much the same exact thing. But I mean, yeah, so don't worry if you're confused about this small difference. It's relatively semantic. Illuminance is really what we're going to be evaluating today, but you'll see that we'll use the same metric, or actually even call it candelas per meter squared, sometimes when we refer to it as luminance. And we'll use that in the next session when we start doing physics-based renderings. And it's the same exact units is the important thing to be realized. It's just measuring it at a different place. All right, and so with that, I mean, we'll get into some stuff later in this, and don't get too overwhelmed by what I'm showing you right now if you haven't seen these before. But essentially, from these three core metrics here of radiation, illuminance, and luminance, we get a whole range of different daylight metrics that I'm going to explain as we get into it. Really, we're only going to cover one today called daylight autonomy, which is probably the most common one. But there's a whole range of other metrics that come out of this that are sort of trying to measure daylight over the entire year, is most of what these things are trying to do, or measure glare probability. All right, so with that was just a really brief refresher. Okay, yeah, I'm not going to get into that rule of thumb yet. So with that, we're going to dive into our actual Rhino model, and Rhino Grasshopper right now. And so you guys will see ARPAN has distributed to you guys a file. This is what we're going to be looking at today. We're just going to be looking at an office with a pretty deep floor plate. And we're going to be looking at how do we get daylight all the way from the window into the back of the space so that the people working back there. I mean, I haven't really shown their desks, but ideally we want the people working back here to have daylight just as much as the people working close to the window. So we're going to evaluate a bunch of different strategies to try and improve the daylight here. All right, so the first thing I'm going to do, you guys will notice that I've kind of modeled all the detailed geometry, and we certainly could run our daylight studies with that, with all this detailed geometry, but for the sake of time, just because this is a 2-hour workshop, I'm going to be working with some simpler geometry here. So basically, we're going to just start by assuming a box instead of all the detailed geometry. And you can use the same methods I'm showing you here to run the detailed geometry if you want. But we're just going to evaluate this box. We're going to evaluate a single window. We're going to extrapolate that up. And then we have a test surface here on the inside, which is essentially the area that we're going to evaluate daylight. And I've pulled it off a little bit from the side just because, we're imagining this is kind of an open office plan, so we don't want too much reflection from the side of the walls, light reflection. So that's why I've kind of pulled it off the sides a little bit there. And importantly also, we also have a ground surface. And you don't always need to model the ground surface if you're fine with a lot of the defaults, but if you're doing, trying to do very accurate studies, you want to look at the reflection of light off the ground. So I've included this in this example here. All right, so that's our geometry, very simple to start off with. And so I want everyone to open up Grasshopper, which actually I already have open here, and just start a brand new file. We're going to build up from scratch a simple daylight model of this office just to evaluate first. Let me go to wireframe. Just to evaluate how deep is the initial question we're trying to answer. How deep does the daylit area actually get? And we're going to run an Illuminance simulation to start off with to try and get a sense of this. So, okay. All right, so I'm going to drag and drop just like I've started all the other files in the series. I'm going to start by dragging and dropping Ladybug onto the canvas. And that's because even though we're using Honeybee, a lot of the components rely on the Ladybug libraries here. And then I'll drop the Honeybee component, which has all the extra Honeybee libraries that we need for detailed daylight analysis, like what we're doing here. Okay. All right, so next thing we got to do is we want to bring in our geometry into Grasshopper. So I'm just going to select this box and bring up an empty geometry parameter and right-click and set one geometry. And you'll see that it will turn green or red depending on whether it's selected. So that's now in Grasshopper. And maybe just to keep track of things, we'll label this like test zone or something, or office zone or something similar. You can label it whatever you want. And you see, I just set it to always draw the name there so that we can see that text, which you might not need to do if you're not using the icon display. All right, so I'm going to turn the preview off here just so we can bring in the other geometry. So we've got our test zone. Next thing we need to do is bring in the window. And so you see by default, we're going to actually test a few different arrangements of windows. But if you guys just look at this layer, initial windows, if I turn it off, it's on and off, it's just a single window here. And we're going to start just by evaluating this, a nice ribbon window right at the level of occupant view, which is probably, what we'd usually design in order to have a good view to the outdoors. All right, so I'm going to set this, I'm going to open this, and we're going to go set one geometry, and we'll label this window. All right, and so we brought that now into Rhino Grasshopper. Next thing we're going to do, let's see, we have to bring in this test surface. Well, actually, maybe let's bring in the ground first. So I'm just going to go select the ground, set one geometry, label that ground. All right. And this is pretty basic. For everyone who's ever run daylight simulations, I'm sorry that this is it's probably a lot of review. And so finally, we're going to copy paste and we're going to bring in the test surface. So set one geometry, and I'll call this test surface. Okay. All right. So now we've got all of our geometry into Grasshopper. The next thing we need, even before we start the process, well, all right. Actually, let's all start processing this. So the first thing we'll realize is that this is just geometry by itself. So there are none of the properties that we actually need for this geometry in order to run it through a daylight simulation. And particularly those properties that we need are things like like the reflectance, things like maybe specularity, if you guys know what that is. We need a few extra properties of these materials in order to be able to accurately run them through daylight simulations. And so what I'm going to do right now is I'm going to take this test zone, and just like what we did with the energy model in order to build our energy models, I'm going to use this Honeybee masses to zone component, and I'm going to connect up the test zone to that, hit a Boolean toggle, set it to true, and now we're going to have, out of this component, we're going to get a closed BREP, just like what we put in. We put in a BREP, we get out a BREP, but very importantly now there are a whole bunch of different properties being assigned. Once we pass it through this component, there are a whole bunch of different properties assigned to the different surfaces, and you can even see those properties if you're curious using the label zone surfaces and connect up those zones. You don't necessarily have to follow this part, but this is just to show you that all the surfaces they have names assigned to them, and very importantly, they have radiance materials assigned to them. So we have these exterior roofs and walls, all these materials being assigned by default. And you see that the component's relatively smart. It knows that if a surface is facing up, it's a roof or a ceiling. It knows if it's facing down, it's a floor, etc. So all right, so we've got all these properties assigned to our geometry, but importantly you'll see that if I were to turn all of this off or just hide the Rhino geometry and preview this, that there's no windows yet on this surface. So the next thing that we have to do is add the windows to it, and you'll see, I mean, because we've already brought in our window here, all that we have to do to add that window is use this Honeybee add HB glazing component. And I'll drag and drop this, and we need to connect up our Honeybee object, which is our zone here, and then our window is basically our child surface, or it's a surface that belongs to the larger zone that we're trying to model. So just like with the energy simulation, if you guys remember. All right, and so now if I turn the preview off here, you see now our geometry we're getting out a single BREP, but it has this window now punched into the side of it. And we can even see, if we really want to check the properties of this window, we can connect up our zone to this component, and if we set windows to true, you'll see that, well, it hasn't assigned, it's assigned actually a default window construction to this window. But importantly, I mean, the window has a name, which we can't read too well because of the tolerance issue. But in any case, yeah, the important thing to realize is that all these things have been assigned. That it knows it's a window, a surface type 5, it's got a name, etc. All right, and maybe we'll go back to seeing what the other surfaces are. Okay, and maybe we'll just do one other thing to make it clear that this is actually a window. So we have another component here called the Honeybee decompose based on type. So if I drag and drop this onto the canvas, and don't worry necessarily about following along with this if you are following along, but if I connect up our Honeybee zone to this, you'll see that it will spit out all the different surfaces that are walls, all that are windows, etc. So if I just hook up a native Grasshopper preview component here, and I plug the window in there, you'll see that it's now got our window surface registered. And so I'm just going to add a simple color swatch to this so that we know it's not this hot pink weird thing, but that's actually a window. All right, okay, so we've got some things here that are actually displaying our zone geometry, our window geometry in Grasshopper. So we know things are being assigned. And all right, and we've got properties on these materials, on this geometry now, so that we could run it through a daylight simulation. All right, the next thing we have to do, we have to take into account the ground. And you see I've showed you one workflow here where you can just take a closed volume and automatically turn it into a room that has automatically assigned constructions. But for something like a ground, if I go back to what's in our model here, our ground, we're going to have to use a different method in order to factor it into our daylight simulation. And in order to do that, I'm going to use this, instead of using the create HB zone component, I'm going to use this Honeybee create HB surfs component. And you guys may remember we used this all the way at the back at the beginning of the energy modeling tutorials. And yeah, and I know I'm going very fast, by the way. Don't worry, ARPAN is recording this, because I saw someone just ask that on the chat window. So don't worry, yes, there's a recording of this, and I go very fast just because I know there's a lot that I want to get to in the short time that we have here. But of course, yeah, especially a lot of the learning, especially that you guys will experience, will happen as you go through the recording. And the important thing is that you just get a general gist right now. All right, I'm going to connect up the ground to this geometry here, to the HB surface component. And you see now it's just like all the other components. It's assigned properties to this. It's assigned it a name, a random name, and assigned it random material. And so, all right, so now we have both a zone with a window and a surface that we can now use to all together in a daylight simulation that have default materials assigned to them. All right, so we're part of the way there, but the next thing that we need to do, now that we have all our geometry with materials assigned to it, is that we need to take our test surface, which is what we have here, and we need to break it down into a set of points, basically, because we don't want to just evaluate the daylight at a single point on the surface. We want to really break it up into a bunch of points so we can see a full gradient of daylight from the front of the zone to the back of the zone. So what I'm going to do right now is I'm going to take this test surface and I'm going to pass it through this Honeybee generate test points component, and which is right under the 3 daylight tab. And I'm going to connect up this test surface to test geometry here. And you see what this does, we have to put in a grid size and a distance from the base of the surface that we want to evaluate daylight at. So I'm just going to, right now, the grid size is just any your Rhino model units. Very importantly, Honeybee right now really only works in meters, so just make sure, maybe check your unit system now, and if it's not, by typing units in the Rhino command bar, and if it's not at meters, I would change it and then recompute the Grasshopper canvas. And so yeah, so now I'm going to put in a grid size in meters here. Actually, it should be in meters because I gave you guys the starting Rhino file. So yeah, so you guys shouldn't have to worry about that. All right, and I'm going to connect up a grid size. Let's say we'll evaluate this at every 50 centimeters. So I'm going to put in a 0.5 meters, and I'm going to connect this up to the grid size here. And then the distance from the base surface, the reason why we have the distance from the base surface is that sometimes you're not using an actual, real test surface that you're pulling out here, but you're just using the floor of the zone, let's say, for example. And in that case, you want to make sure that you offset the points from that floor surface because desk height is quite a ways up from the floor surface. And a lot of the times it will tend to put it about 80 centimeters above the floor. But in this case, because our starting surface is already above the floor, I'm just going to put in a distance from base surface of 0. And that'll generate the test points right at the surface. And you see by default the preview is off on this component, but if I right click and turn the preview on, you'll actually see all those test points where we will evaluate daylight very shortly. All right, and this is a pretty good gradient. This shouldn't take too long to calculate, and we can even see if we hover over it. It's about 702 test points. And this is going to be manageable for the Illuminance simulations that we're running. It will take a few seconds. All right, so we've got our test surface set up. We've got, let's see, we've got our zone set up, and maybe I won't display the ground here. Maybe I'll plug in, yeah, I think it's nicer to label the zone. We've got our geometry set up, and maybe we'll put this all together here. So we got test surface, we got our geometry with material properties, and now I would ask someone, from the audience, if this was more interactive, what will we do next? What else do we need to actually run a daylight study? And one of you smart members in the audience would say, well, we need to actually have the weather data. We need the climate data, and we need some type of sky that we're going to be simulating the daylight with. All right, and so right now I'm going to bring in a weather file. Let's see, I know I've been working a lot in like Boston. Let's see, we've been using weather files from a few different areas, but I'm going to use this Ladybug download EPW weather file and connect the Boolean toggle set to true to it. And this will open up a map. And I would say let's pick a place where there's a lot of sun and I know we can really get some good daylight. And so I'm going to pick, let's say, somewhere in sunny California. Maybe we'll say San Francisco. And I'm sorry, yeah, you guys should feel free to also if you pick, whoops, I'm spelling that completely wrong. You guys should feel free to pick any weather file you want, but I'm just, I'm typing in San Francisco here. Yeah, certainly some other different climates will show you some more interesting results. But I'm just going to pick this TMY3 San Francisco file here by right-clicking and then right-clicking there and copying. And let's bring that weather URL is going to go into our Rhino Grasshopper file now. So I'm just going to bring that in by double-clicking the canvas, hitting quotation marks, and pressing Control-V to paste it into a panel and hitting Enter. And so this has the URL to that weather data. Now I'm going to download and unzip that weather data using this component here, this Open EPW and Stat weather files under the Zero Ladybug tab. And then I'm going to then we're going to essentially have that EPW file within our canvas, within our Rhino scene. All right, so we're now ready to actually we don't just need the weather file itself, but if we're going to be running an Illuminance simulation, we actually have to unpack this weather file and unpack the data inside of it and produce a full, what we call a sky, in order to be able to assess what the illuminance is for a given set of situations. So in order to make a sky right now, I'm going over to the Honeybee tab. And you'll see that we have a whole section here, a whole 2 daylight section for just generating different types of skies, as well as also generating the electric lights, which we're going to use later. So I'm just going to connect up. I'm going to grab a Honeybee Generate Standard CIE Sky here. I'm going to drop it on the canvas, and you'll see that it takes as an input our weather file, and we just need to now connect up a month, a day, and an hour. And a sky type in order to be able to simulate this. So our month is going to be, let's say we'll just pick something right in the middle of the year. So we'll pick right on the equinox. Maybe I'm just going to double click, hit quotations and type 3 and then enter. And then this we'll start on March. And so if we're going to do the equinox, we need March 21st. So I'm going to copy paste that panel and then connect up a 21 here for the day. And then maybe we'll just do straight up at noon. We'll evaluate, kind of maybe one of our better scenarios for daylight. But yeah, I mean, it's in the middle of the year, and we'll put it at number 12 in order to indicate noon for our hour of the day. And then finally, there's one last input that we need to input here, which is you can tell it's required by the fact that there's a single dash in front of it. That's our convention in Ladybug and Honeybee. And so we'll just do a sunny sky, nice sunny California sky. So I'm going to do a 0 right here. I'm going to copy paste that and hit a 0 and then connect that up to sky type. All right. And so now you'll see what has happened is that our weather file, based on the inputs that we put here, has transformed into a .sky file. So this is actually a file that has all the information of what the sky is like at this point in time. And you guys don't necessarily have to follow what I'm showing here, but it's important that you guys understand that exactly what the sky is. So we can convert the sky using this Watch the Sky component. I can convert it into an HDR image or a high dynamic range image if I just set a Boolean to run it here. And really don't worry about following along with this. This is just so you guys know what the sky file actually is. And so now we have an HDR file path that is actually an image file, an image that has actual illuminance values in it. And I'm going to convert this over to a GIF image so that we can look at it. So I'm going to use an HDR to GIF, which is in the 4 tab here. And then we're going to see that this is now a GIF file on our machine. And then finally, I know you guys probably don't have this component, but you can actually go and open up this GIF file if you want to see what the sky looks like. I'm going to use a special component from another plugin here called Embryo that just allows me to see an image within the Grasshopper canvas. Very good plugin, Embryo. I'd recommend you guys look it up. And you can see this is what the sky looks like essentially. It's essentially just got one big sun in the south part, and it's darker. It's a nice smooth gradient over the whole sky. So really what we've done here is we've taken just the raw weather data and we've produced a sky that we're going to simulate with, run a daylight simulation with. All right, now that's really a bunch of extra stuff there. So don't worry really about simulating what the sky looks like. We'll just move that off to the side. The important thing is that we have the sky file path right now. All right, so we've got our test points, we got a sky file, we got our geometry. I think we're pretty much ready to run it. So all right, let's make Grasshopper nice and big right now because we're going to work just with Grasshopper now. So the next thing we need something that takes all this information together and puts it into a set of instructions for a daylight simulation. And specifically, we have a whole tab called the 3 tab over here, the Daylight Recipes tab. And this is all just about making recipes for daylight simulations, making sets of instructions for daylight simulations.